Okay, let's go ahead and get started. Thanks for coming back, everyone. I loved talking for the first 45 minutes here about what science looks like on paper. I'm very excited to spend the next 45 minutes to talk about what science looks like in practice. We're going to get to take a look at a couple of videos in this next session. If you are not joining us live today, please make sure that you have watched the opportunity myth session first, and then also the grade appropriate assignment session for science next, because this third session builds on understanding from the previous two. So if you haven't done that, pause here, go back, and then come back and join us at this recording once you've done those first two. And then you'll have all the information you need. And so for folks that are here and for everyone who's watching later, let's go ahead and dig in. I'm going to show these norms again, although everyone's doing a great job following them. But I want to give you a second to get yourself settled before we take a look at some of the tools and the materials for this session. So use this as a quick reminder to close out anything that you don't need, to make sure that you're on mute, and then we'll get going. Okay, here is thanks, Krista. Last logistical thing here is the link for the materials for this session. If you go from that link, it will take you to the folder for this session on strong instruction. There's just two documents in there. One is a repeat from the session on grade appropriate assignments. It's just another quick access to that Tennessee Science Standards reference document. And then also the tool that we'll be using to ground our session here today. So I'm going to go ahead and grab those and get those open. I'll give you a second in case you are typing or you're trying to use the QR code. All right, so here are our goals for the next 45 minutes. We are gonna follow a similar process of using the TNTP science walkthrough tool to ground us in a vision for excellent science instruction. This tool can help us to internalize what strong science instruction looks like. And after we've gotten familiar with the tool, we'll use it to help us analyze practices in instructional practices in science that engage students and practices that help students to own their own learning. And then finally, we'll connect that back to the larger work of STEM.LD. So before we dig into the tool itself, I think it's important that we are all grounded in what we are seeking to achieve through STEM instruction in our schools. So I have invited one of America's favorite scientists, Neil deGrasse Tyson, to help us better understand the important role that science education plays in our society. And so as you watch this video, what I'd like you to think about is what are the implications for how we think about science instruction in classrooms based on what he says here about the role of science education. I'm going to hit play, and if you can hear it, just give me a thumbs up so I know we're good on sound.
When I think of science, I think of a truly human activity, something fundamental to our DNA, something that drives curiosity. When you're a kid, you're born a scientist. What does a scientist do? We look up and say, I wonder what that is. Let me go find out. Let me poke it. Let me turn it around. This is what kids do. Kids that can barely walk, what are they doing? They're turning over rocks. They're plucking petals off a rose. They're exploring their environment through experimentation. That's what we do as human beings. So what do? We prevent that. We prevent these depths of curiosity from revealing themselves, even within our own residences. You know, we spend a year teaching our kids to walk and talk, and the rest of their lives telling them to shut up and sit down. What kind of environment is that? The goal here is not to make everybody a scientist. That's not the goal. What a boring world that would be. You want artists, you want musicians, you want novelists, poets. You want the rest of this. What matters is whether they're scientifically literate and maintain that literacy and that curiosity throughout their lives, no matter what becomes their profession. People think science literacy is being able to recite facts, and it's not that. It's a part of it, but it's not the main part of it. The main part is, how do you look at the world? What does the world look like through your lens? If you're scientifically literate, the world looks very different to you. It's not just a lot of mysterious things happening. There's a lot we understand out there. And that understanding empowers you to first not be taken advantage of by others who do understand it. And second, there are issues that confront society that have science as their foundation. You can't look at science and math as some separate subject. It's fundamental to what it is to be alive because it's all around us. And it influences your health, your safety, how you're gonna have to vote, what issues are before you politically. If you're not scientifically literate, it's in a way you are disenfranchising yourself from the democratic process.
But my favorite part of this video actually is the part where he talks about how we need artists and poets and musicians, and that the goal isn't to make everyone a scientist, but the goal is to make everyone scientifically literate. And that means that you're not just able to cite facts, but you're able to critically look at the world through your own lens. And so if we know that the goal is not the memorization of facts or even just the repetition of facts, but the goal of scientific literacy, that has implications for how we think about the way that we teach science in our classrooms. So to create scientifically literate communities, students, when they're children, need to have access to all of these 4 key resources in their STEM classrooms. And strong instruction, this goes from the opportunity myth, and strong instruction is one component of this framework. And so we need to know, just like we do with grade appropriate assignments, we said, what does it look like on paper? We need to know what it looks like in practice. What does strong science instruction look like in a science classroom? Oops, I clicked one too far. So we've got a tool for that. So to help us understand if students have access to strong instruction, we can use the instructional walkthrough tool in science as the foundation of our vision for what strong instruction looks like in science classrooms. This tool is in your folder with your materials. So if you would take a minute to open that up, and then I'm going to give you about 90 seconds to read over that tool. Make a note of any language that sticks out to you or write down any questions that you have as you review it. So I'm going to give you, like I said, 90 seconds, and then we'll talk about what you see there. Okay, so just like for the grade appropriate assignments tool, our goal is not to be normed raters today, but to use this tool as a foundation for what we expect to see in a strong science classroom. And we're going to use the language of these indicators to help us internalize that. So you probably saw that the first section of the tool was about culture of learning. We're not going to spend a ton of time talking about that one today because all of the classroom videos that we're going to see are strong examples of classroom culture, but I want to make sure that you make sure that we gave voice to the fact that this comes first on the tool. And so by culture of learning, we're considering, like, are students doing what's being asked of them? And we generally look at this first, because if kids are not mostly on task, they're not focused on the work of the lesson, then you may need to focus on classroom culture first before addressing, or simultaneously while also addressing the content of the lesson. But it needs to be not overlooked when thinking about the strength of the classroom, strong instruction itself. But we're not going to talk about how the classroom culture looks in the videos we're going to look at today, because they're all strong examples. Okay. So next, we consider if students are working on science content that reflects the instructional shifts that were articulated by the standards. If you look at the language of these indicators, you're going to see that they're very similar to the language of the indicators that we consider in the content section of the grade appropriate assignment. And that's because we know that if students aren't working towards rigorous grade level standards, the rest of what's happening doesn't matter. As we talked about in the grade appropriate assignments, the standards build intentionally within and across grade levels to prepare students for college and career. And therefore, in order for a classroom to have strong instruction, it has to be focused on the correct content first. So we're going to ask ourselves 2 questions to see if the instruction is strong science instruction. And the first that we're going to look at is whether or not the instruction is focused on, similarly, making sense of a phenomenon or solving a design challenge. And we have already defined what that was as an observable event that we can use scientific knowledge to explain. And then we're going to ask ourselves, does the lesson focus on the development of the cross-cutting concepts, the disciplinary core ideas, and the science and engineering practices? And so when we talked about grade appropriate assignments, we didn't talk too much about what it should look like to use the practices or the concepts, but we are going to see teachers using those in the videos that we are looking at today. So we're looking to see during the lesson, are these 3 ideas intertwined into how the teacher has developed and is executing the lesson. So let's take a look at classroom. The classroom that we're going to look at today is also is another 8th grade example. And so I want to give you a second to read the standard that the teacher is targeting. We're not going to, like, watch it and then go back and guess the standard. I'm going to tell you up front that this is the standard that the teacher has been targeting for this video that we're going to watch. So take 30 seconds to read that so you can have an idea of what you may expect to see in this video. And so this video that we're going to look at is the beginning of a unit on plate tectonics. So if you were reading the standards and you're not super fluent in your earth science, there may be a lot of words in that standard that you're not super proficient at, like asthenosphere and lithosphere and seafloor spreading. But this is an introduction to which I think we all can access this introductory lesson on plate tectonics. I'm going to tell you what kids did before we watched and then where we're jumping in. Because we're not going to sit and watch a full classroom observation, which you would probably do if you're using this tool. You'd watch a big chunk. We're just going to watch a few minute snippets. So I want you to know what's happened previously. So prior to this video, kids watched a video of called A Scary Day on Mount Everest. And it was about an earthquake that was on Mount Everest. And then they read a news article about that, that day on Mount Everest. As they explored both of those artifacts, they filled out a chart for what they noticed and what they wondered, and then they discussed it in small groups. So we're going to pick up in the lesson where they've finished with a small group conversation, and now they are discussing with the whole class. Okay, and I'm going to play the video, then I'm going to scoot it to the 3-minute mark, and that's where we're going to watch to the end. So we got about 4 minutes, and so as you're watching it, I just want you to consider what we saw in the language of the content indicators.
Mount Everest keeps growing each year.
Say more.
Like, I don't know how it does grow, but it just keeps growing. And after the earthquake, the mountain shrunk by 63 centimeters, almost 2 feet.
Yeah, I was talking with Maya's Halo about that. That was back in the 1934 earthquake, right?
Yeah.
Right, but you said it gets taller each year? What does that mean?
It just grows.
It grows. Interesting, and then you said what?
And then, like, after the last major earthquake, it shrunk.
Yeah, but then you said a question. You were like, I don't know what.
How it grows?
Yeah, isn't that odd? Wait, so mountain grows taller, right? At the same time, the mountain moves towards decks, and then at the same time during this event, it did what? It went what? Talk to me. Move back, right? Okay, cool. Anything else you guys found from the reading or anything like that? I've heard from these people, but I'd love to hear from somebody I haven't heard from. Joey?
I put in my wonder what causes Mount Everest to move.
Oh, cool. Okay, great. So do we want to just jump to the wonders? Well, cool. You said what causes Mount Everest to move? Excellent. What else were we wondering about? Max?
What causes it to shrink too?
Yeah, like weird. It moves, it shrinks. Dex?
Why did it go southwest?
Why did it go southwest, right? When it was like perfectly happy going northeast, right? Not that it's happy, but you know what I mean. Go ahead, Miles.
So if we're still like alive, like humans, in a billion years, if it keeps on growing, would it get like to the height of the moon?
I don't know. That is a really interesting question. Interesting. Margaret?
Isn't the tallest mountain in the world actually an underwater volcano?
So what?
So like,
How does this relate? I'm confused.
because it says that Everest is the tallest mountain in the world, but I've read at Queens and other places, I've read that the tallest mountain in the world is actually an underwater volcano by Hawaii.
Does anybody have a question about what Margaret just said? Because I thought this was all about Everest.
Yes.
Tiff?
Is a volcano a mountain?
Great. I don't know. That's a great wonder. Did you write it down? Olivia?
Well, I mean, I think we're talking about above sea level, but it's under sea level. It doesn't really talk about on the earth. Like, still on the earth, like, but still on plates.
What are those?
Like, plates are the things that cause earthquakes and volcanoes.
So let me just make sure I heard this right. Olivia, you're saying this has nothing to do, like what Margaret's bringing up is below sea level, but Everest is above sea level.
Yeah.
So when it's above sea level, it's a mountain. When it's below sea level, it's a, what? A volcano. Okay. I don't know. Yeah, I'm just as confused as you are.
Okay, so this is a strong example of a teacher who is grounding their instruction in a phenomenon. Sorry, let me go back because I didn't want to see the YouTube. There we go. So like kids weren't just introduced like, hey, this is our first day on tectonic plates, or let's like talk about what let's define.
Do you guys know this?
Let's not define what a tectonic plate is. Instead, they were put in the real context of the situation. So they didn't just, she didn't even just give them the facts. This is what happened on Mount Everest on this day. She had them actually experiencing it by watching the video, reading the article. And they were also asked to make sense of it. So it wasn't just presented as the phenomenon, they're asked to make sense of this phenomenon by sharing their noticing and their wonderings. And you heard kids make a lot of connections to previous content. There was a student who already knew about plate tectonics and she brought that, and that was surfaced. There was another student who talked about prior knowledge of underwater mountains near Hawaii. And so kids had an opportunity to see the phenomenon, to experience it, and then also to engage with it on their first day of this unit. So that's definitely it's a yes for that indicator. It's a strong example of a phenomenon in practice. Let's consider the second question, which is, does the lesson focus on the development and use of grade appropriate science and engineering practices, disciplinary core ideas, and cross-cutting concepts? So I'm going to ask for your participation on this one too. So you saw these science and engineering practices in our last session. Based on what you saw in the video, We want to try to figure out, oh, I gave it away. I was going to ask you to share which science and engineering practice you thought it was most aligned to and why. This progression chart that I clicked ahead to comes from the Tennessee Science Standards document. And that is also in the folder there for you. It's on page 27 if you want to check it out and look for yourself. And so we saw kids in this video using the science and engineering practice of asking questions. You can see it's asking questions for science and defining problems for engineering. And if we can use this progression the same way we use the core idea progression to like clue in on the science practice and the grade band of what it should look like. And so for 6th through 8th graders, like the way kids should be asking questions in 6th through 8th grade is different from how they're asking questions in K2 or 3-5. And these progressions are really helpful for us to understand what does it look like at that age. So for asking questions, the question should originate based on their experience. And the question should lead to explicit relationships between variables. And this video is a good example of that. We heard kids talk about their experience, their prior knowledge and their prior experience as how they were coming up with their questions. And we also heard kids start to talk about the relationship between the height and time and the relationship between the event and the height of the mountain. So did the mountain get taller or smaller based on the earthquake? What rate has it been growing with over the course of time? So this would be a strong example of using the science and engineering practices for this grade band. Okay, disciplinary core ideas. I'm gonna try really hard not to click ahead this time to give you the answer. So for the disciplinary core ideas, based on what you saw in the video and what you actually might recall from the standards, which of these core ideas is this video focused on? Is this lesson focused on? And you can type it in the chat. One answer from Olivia. Let's see if anyone else has a different idea. Great. Thanks for that agreement, Philip. Yeah, so we are working on ESS2 Earth systems. Let's now see, are we working on Earth systems at the right level of depth for this grade? And we can use the same appendix that we looked at for grade appropriate assignments to help us understand if it's at the right level of depth for 6th through 8th graders, if it's focusing on the right key ideas. So, I don't know if this is linked in the folder for you. It was linked in the grade appropriate assignments folder, and it's not there. I'll throw it there for the future. But we can use this appendix E from the framework for K-12 education to help us understand what the disciplinary core idea looks like for 6th through 8th grade. It is aligned to ESS2B, which is about plate tectonics, and I'm using plate tectonics as the unifying theory that explains the movement of rocks at the grade level. So today, we don't hear her using plate tectonic theory language. It's the first day. So, but we can see that there's a connection between what she's doing and what she's preparing them to tackle in future lessons. Okay, and then the third element we want to talk about is the cross-cutting concept. Same question in the chat. Which of these cross-cutting concepts did you see in practice in this video? Or which were relevant to how the discussion played out? So we've got 3-4 votes for cause and effect so far, which is great. I agree, cause and effect. We saw that this is the first day. So students were not yet naming the cause, but they were identifying the effect. They weren't sure what was leading to this change that they were seeing, but there was an effect that they were going to, or they were hypothesizing about the potential cause. Back to that Tennessee Science Standard, there's really nice progressions for the cross-cutting concepts in there as well. This one from cause and effect is on page 21, if you want to click back to it. And again, just like the science and engineering practices, it helps us to understand what is the level of understanding of this theme that kids should have at this grade level. So for cause and effect in grades 6 through 8, kids should begin connecting their explanations to specific scientific theory and use those relationships to make predictions. In the video we watched, we heard that kids were identifying the effects and they were wondering about the causes. Since this is the first day of this unit, students, I think, are actually not yet demonstrating this cross-cutting concept at the full demand of the grade band because they are not using that specific scientific theory to back up as the cause of the effect that they're seeing. They do have an opportunity, though. If we think about what we saw overall in this video, there is integration of the content, the practice of asking questions, and the cross-cutting concept of cause and effect. We see all three of those dimensions in play here in this short video. So for that reason, this video would get a yes. It's a strong example of phenomenon-based learning, and it has integration of the three dimensions. And so it's a pretty good example of what we'd want to see in a classroom when we're looking at science instruction. So let's move on then to talk about the practices. The other two sections, the next two sections of the tool, which are on instructional practices and on student ownership. So when we think about high quality, after we think about high quality content, we look to see if the teacher's instructional practices support all students to learn the content at the depth of the standards. If you look at the language of the indicators, if you have the tool out there, you can see some of these best practices that we've listed as instructional practices for science. And so these instructional practices in the walkthrough tool are research-based teacher actions that support students in making sense of science. One of those, as an example, is that a teacher leverages students' prior knowledge and experience. And we heard that in the discussion, and this is an anchor chart from later in that lesson. Anchor chart is a chart the teacher created with students later in that lesson, where they listed out other phenomena that they thought might be connected to this article and news report that they read about. So they thought that it may also be related to other earthquakes around the world, or to tsunamis and to avalanches. And so this teacher is explicitly and intentionally leveraging students' prior experience and knowledge in order to help them make sense of the science. And so when teachers do that, when they intentionally connect to relevant and prior experiences, teachers help students to understand the content, the knowledge and context, and then internalize the interconnectedness of what they experience in their world, which is essential if we're talking about developing scientific literacy. There's a couple other indicators there that I wanted to highlight for you for practices, for high quality instructional practices that help students to engage in the learning at the right level of depth. And those are using multiple explanations and representations or models, deliberately checking for understanding and making necessary adaptations, and then summarizing the learning throughout the lesson to reinforce the focus. And we saw the beginning of the lesson here, so we didn't see the teacher at the end summarizing what is the important knowledge that we've gotten to at this point for this day, and then making sure that all kids get that before they move on to the next day in their learning. Those are three additional instructional practices that are key to students having strong instruction in science. I also wanted you to be able to take a look at the student ownership section of the instructional walkthrough tool. You can look at that with the indicators that are on the slide, or you can look at the language of the tool itself. The last thing that we look at when we're thinking about strong instruction is to see if students are responsible for doing the scientific thinking in the classroom. And what that looks like in practice is that students are expressing their ideas, they ask questions about each other's thinking, they share their thinking as it currently is, and then they revise and refine that thinking when additional knowledge causes them to reflect on their prior understanding. And then they also, lastly, use scientific language as appropriate for the content in their written explanations and discussions. And so today, in the view of the first video we watched, we didn't hear a ton of scientific language. They haven't developed the scientific language yet to be able to speak about this content. But as students progress through this unit, we should expect to hear them using some of the more language from the standard and the language from the theory of plate tectonics as well. Okay, so we're going to watch another video and this time we're going to take a look at the practices and the student ownership. We're not going to think about the content. We've had practice with that in the first video and in our other sessions. So now we're really going to focus on what do strong instructional practices and what does strong student ownership look like in a classroom. So we are going to watch a high school physics classroom. And as you watch, I want you to make note of the indicators that go under instructional practices and student ownership.
As you wrap it up in the next 10 to 20 seconds, finish writing what you're writing. Now here's what I'd like you to do. This part of the lesson is going to be observation. That means I want you to look at the demonstration. You can get out of your seats. At this time, I don't want you writing. I'm going to give you plenty of time to write about it, but first I want you to see it. I want you to come up here in a position where you can see the demonstration, so you can get out of your seat if you need to. And I have 2 beakers. I have one beaker right here with a thermometer in it that reads 80 degrees Celsius. And I have another beaker right here with a thermometer in it that reads 21 degrees Celsius. So just to be clear, I have one that reads 80 degrees C and one that reads 21 degrees C. So I'll call this T sub H, and I'll call this T sub C. Of course, T sub H stands for the hot, and T sub C stands for the cold. Both of these are water, and I would like you to observe what happens. I have some red dye. I'm going to drop it in there, and I want you to observe what's going to happen. I'm going to tell you what I'm not going to do. I'm not going to stir it. So just watch for a moment. As you're watching it, you can turn to the people in your group and just make observations. You can say anything you want. Just watch what happens.
Way faster. Hold on. Some sort of that one oh, you know what? I get it. Because the atoms are moving so much, it's kind of stirring itself. It's like, what do you mean by stirring itself? It's not stirring itself, but the atoms they're moving so much that it spreads it faster. Okay. Than this one.
All right. All right. What do you notice happening here? What do you notice happening here? Go ahead.
The dye dispersed faster in the hotter water than it did in the cooler.
Okay. So what?
That's just the difference. The difference is that the hotter the molecules get, the faster that they move around in the beaker. So if you put...
Which molecules?
The water molecules.
Can you see any molecules in there?
Well, no, but, you understand that because when you put the dye in, it shows how they're moving around the beaker.
What's he talking about, Melanie?
He's talking about that when you put another substance in another liquid substance in a water, the atoms are moving faster. So in this case, when it's hotter, that they're going to diffuse faster because the atoms are moving faster than the atoms that are in the cold.
Can you see any atoms in there?
No.
Then why are you so sure that atoms are going on?
Because of atomic theory.
Tell me more.
Atomic theory says that everything's made up of matter and atoms in it.
Okay, I want to be kind of clear. That's correct. Here we're actually talking about molecules. Which molecules in particular?
Water and oxygen.
Water, hydrogen and oxygen atoms that come together to make water molecules. And we can't see those. We can't see them at all. If I look in there, it looks like liquid to me. If I try to see particles, I simply can't see them. But the dye helps us to infer something. And it's helping provide evidence for the model, the atomic model that you're talking about. And I would like you to take a moment right now to sit down in your groups and discuss what kind of evidence did this observation give you about the atomic model or the molecular model and temperature. So sit down for a moment and give that a discussion.
The way I thought, like you can picture it, like just imagine there's like a bunch of tiny little balls in the water, and since when it's hotter, they're moving a lot faster. So imagine just dropping something into all that, you see the balls just moving the liquid, the other liquids that were dropped in there around faster than this one. Yeah. Here they just fall and they can just move throughout, and they won't diffuse. They won't diffuse as fast as temperature.
Okay, guys, let me be clear. This is a talking time, not a writing time. I'm going to ask you to write in a moment, but first I want you to talk. So the question is...
Okay, that's the end of the video. Such a great fun.
As you wrap it up in the next...
All right, so let's talk about both the instructional practices and the student ownership. And so you can share your ideas in the chat, or I would love for you to come up and share some of them with the group so we can hear them. Let's talk about the instructional practices first. What evidence did you see of any of these instructional practices in the video?
They definitely had the explanations and the representations through the modeling of adding the dye to the water.
Yeah, thanks for getting started, right? So we saw him draw the representation on the board of the two beakers, and then we saw the representation with the beakers itself and the dye. What else? I see Diana uses prior knowledge. Are you able to come off mute and tell us what you mean? Like, where did you see him use prior knowledge?
I noticed that he was questioning his students about their understanding of the water molecules. And the one young man speaks up and actually gives a statement about what they've learned in the past. And he is pulling it out of him, out of his students is what I see.
Yeah, he does a great job clarifying the use of academic language as it connects to prior knowledge. So someone talks about molecules and he digs at that, right? Like, what do you mean molecules? How do you know there's molecules? And then same thing with atomic theory. Someone's like, well, you know, because of atomic theory. And he's like, what do you mean atomic theory, right? So he is using, I think that's a good example of multiple of those practices, right? Like he is pulling out their prior knowledge. He's deliberately checking for understanding when he asks, like, what are the molecules? And the kids respond that they're the H2O, the water molecules. Yeah, so he's checking for the understanding. He's reinforcing and making sure that they have that correct understanding of atomic theory before he sends them to the group. So we saw him in this like 4-minute video do a really nice job of using most of these instructional practices with this demonstration. Let's move on to talk about student ownership. What evidence did you see of student ownership in this video clip?
They were really trying to explain their ideas and whatnot while they were during the talk session, and he's really wanting to make sure that they talked amongst themselves. Like he was saying, this is a talking time, not a writing time and things. I really like that.
Yep, there's a lot of good stuff there, Philip. I'm gonna pause my explanation. Let's see if anyone else wants to add before I enthusiastically agree. What else did you all see? Kim, you want to talk to us about student talk and how it was productive?
Well, it was productive because they were doing the majority of the talking. The teacher just interjected questions to facilitate what they had to say, and each student built off of the other. And the fact that all students were on topic and truly engaged in the process, you know, nobody seemed off task. Nobody was exempted from the conversations. It was just very productive and meaningful, and they were using prior knowledge well in their discussion.
Yeah, I think like it's still, we watched this video a bunch of times, it gives me like a little bit of goosebumps. So he's like, I want you to watch and then I want you to talk. And then they watch for like 15 seconds and then they just organically start like enthusiastically talking to each other and prompt them and have to repeat the question. They have built a strong habit of sharing their ideas and defending their ideas with each other. So then you can hear them asking questions of each other's thinking, and you can hear him asking, prompting kids to add on, maybe if a student he knows has a good idea or maybe doesn't speak up first. There's a student who said something and then he turned right to the other girl and said, what does he mean when he says that? And she builds onto the idea initially, which is deepening everyone's understanding through the conversation. And I love that you picked up about the last little bit at the end where he says, like, this is a talking time, this isn't a writing time, right? Which is hinting to us that they are having this discussion right now, but then they're going to need to take their knowledge and put it into written explanations as well. So kids are clearly owning the vast majority of the heavy lifting of the thinking in this lesson. And he's there as, and someone said this in the chat, like said this as a facilitator to prompt or to direct the conversation, but not to lead or to do the work of the thinking himself. So this, of course, is a strong example of instructional practices and of student ownership in the classroom. Okay, so that takes us, that's our quick overview of the science instruction tool, and you're just beginning to get familiar with the language of the tool and how you could use it to help you understand what strong instruction looks like. And we spend some time really exploring the standards and the structure and purpose of those. So as we get close to the end here of our time on science today, I would like to take the last couple of minutes to talk about these questions here and hear your thoughts about what you've learned over the past 90 minutes. So what are your thoughts on how science instruction, strong science instruction, prepares students for the future? And if you were going to write your own, maybe you have your own, if you were going to write or share your vision for excellent instruction in science, what would you want it to include? And you can type an answer to the chat or feel free to share with others.
Is it cool if I speak? I prefer to talk.
Of course.
Just, I feel like with science, I always feel like student engagement is like a must and a real big part of it. Even for students that don't have like a strong background when it comes to science, like I say, it's not their favorite subject. As long as you can keep them engaged, I feel like they got a better chance of learning. And then taking like what he was saying earlier in the first video we watched by Neil, that, you know, with the engagement and being involved, they learn the science literacy, which makes them always kind of wonder and question everything. If you can keep them engaged in your class that way, then they'll always want that ability to question and further learn on everything they're doing. So that kind of helps with further their learning, not just for science, but for anything that they're taking upon.
Yeah, and I agree. And I think like the use of grounding content in a phenomenon is a nice way to get kids engaged, to spark that curiosity, to keep them interested. And when you think about balancing the content and knowledge of the core ideas with the practices and the concepts, you get kids doing more. They're more active in the process, which helps them to build their understanding of the way science actually happens in their community. Olivia, do you mind sharing a little bit with us about safe sharing of ideas? That's an interesting point.
I generally do this in my classroom. I do that same experiment, and I will have my students use whiteboards in groups, and they'll talk about their whiteboards. But some of them are just not comfortable talking like that in front of other students, and I really want them to feel that their information, their ideas are just as valued as the students that want to speak all the time.
Mm-hmm. That's great. Yeah, and helping students to understand that like science doesn't happen. Science discoveries and explorations are not a straight line, right? That like we test out ideas, we make mistakes, we learn from those. And so sharing our ideas in writing or in speaking with each other, it's helping us all to develop and enrich in our science knowledge is really important. And so I think it's like important if we're going to prepare students for the future, we need to think about developing this true scientific literacy that Philip was just talking about. And that extends beyond the memorization of facts. STEM careers require students to be able to think critically and make use of their scientific knowledge. And if we only focus on the retention of information, we underdevelop students' abilities to do science and to engage in scientific thinking. which has huge implications for the future and how our students become productive and active citizens. And so that wraps up our time exploring what strong in science education looks like, both in grade appropriate assignments and in strong instruction. So that takes us to a survey right here. And Krista, if you're gonna put the link in the chat, you've probably done already, you have. If you take a couple of seconds, a couple of minutes to fill out that survey, that'll track your attendance too. And then we will again take our break and we will come back together at 3 o'clock to talk about high expectations and engagement. And I will hang here and happy to answer any questions that you have about the content of these first 2 sessions. I've also put my email address there. So if you want to copy that down and reach out to me to talk more about science, that would be quite a delight. So thank you all for your participation today, and feel free to drop any questions in the chat or come off mute if you've got some.